Okay, welcome to lecture here. We're going to continue on with the chapter we've been talking about. I think it's 5-ish. Talk about types of reactions and all those kind of things.
Hey, Professor.
Yeah.
Is there somewhere in the syllabus that says when the exam 2 will be?
Yeah, it's on the schedule. So it's actually, I think it's actually on the schedule in the lecture part. So it's a week from, not a week. Think it's, I think it's a week from today, if I'm not mistaken. Should be a week from today.
Thank you.
Yeah. Yeah, so I think exam 2 is actually is for a weird reason. Usually, like when we're in person, we sometimes have labs and stuff. So that one ended up being on the lecture schedule. So if you look at it, and I think it is a week from today, if I'm not mistaken. All right. Other questions on any of that there? Okay. So we were talking about in this chapter, which again, just a reminder, what we're talking about now is not on the exam. I don't believe. I believe the exam, I probably shouldn't do it off the top of my head here, but I think the exam ended with like the nomenclature and moles and all that. I think an empirical formula. So I think that was the last material that was on the exam. So again, this stuff should be on exam 3, what we're talking about now. Okay, so we started talking about reactions, chemical equations, and stuff like that. So just a reminder, obviously, when we write a chemical equation, we want to make sure that we always use proper formulas. You want to make sure that you get all the proper formulas down first, and then you want to make sure that you balance it. So as we talked about last time, when we do balance an equation, the only thing that we change is the coefficients that are in front of the formulas in the equation. So we want to balance everybody using coefficients until ultimately we do have the same number of elements on each side. Remember that there's really kind of two things when you balance an equation that you want to make sure sort of happens, and that is you want to make sure that you use all whole numbers when you balance the coefficients. So we talked about last time that you can use fractions to balance an equation, but you do need to clear it when it's all said and done. And when you have your final balanced equation, it does need to be whole numbers, and it does need to be the simplest set of whole numbers. So we also talked about last time, again, if you sort of balance an equation with a set of coefficients that you could then go back and sort of reduce everybody down by a common number, you should do that. So simplest set of whole numbers, everybody needs to be whole numbers. Again, can use fractions to balance, but you do need to clear them. Also, we talked about the idea that a lot of times if you do have some of those polyatomic ions that are present in the equation on both sides, it's sometimes a lot easier to sort of balance those guys as sort of whole units rather than maybe going element by element, a lot less sort of multiplying in and things of that nature. Any questions on balancing equations or any of that stuff that we sort of talked about last time? Okay. So what we're going to talk about pretty much for the rest of this chapter here is different types of reactions. So different ways to classify reactions. As we'll see, there's actually, many different ways you could sometimes classify even the same reaction. So we're going to talk about different ways you can sort of classify reactions, different types of reactions, so you can hopefully recognize those. So the first thing we're going to sort of talk about here is electrolytes and sort of what electrolytes are. Electrolytes are really substances that when they go for sort of a swim in solution, they will break apart into ions. And when they break apart into ions, that's really important because it is the presence of those ions that help it sort of conduct electricity. So it can conduct electricity because you have all the positive and negative guys floating around in the solution, helps sort of complete the circuit, if you will, and able to basically conduct electricity really well. As we will see here very shortly, there's sort of three types of electrolytes. There's a strong electrolyte, which breaks apart 100% and produces a lot of ions. There's also weak electrolytes, which, as we'll see in just a second, mainly stays together. But it is still able to produce a few ions, so it's still able to get a few ions in there. So it's able to conduct electricity. And then we really have a non-electrolyte, like it says up here on the screen. A non-electrolyte is a substance that, you know, when it does dissolve, it basically will not conduct electricity because it pretty much does not produce any ions. So this non-electrolyte will not conduct electricity. And it's really because there's no ions. So even though it may dissolve, so, you know, a very sort of common example would be something like sugar, for example. Sugar is basically made up of carbons, hydrogens, and oxygens. And as we know, if we take some sugar, it definitely will dissolve in water, but it will stay together because that's a molecular compound. So you won't produce any ions, no ions. You pretty much get a non-electrolyte. One very common test for electrolytes, like in the laboratories, you take like a light bulb like we see here, hook up a couple of electrodes and basically stick it into these different solutions. As we can see here, this is a non-electrolyte solution. Light bulb is off, does not shine at all. Again, really not conducting electricity because there's really no ions that are present. So no ions that are present in the solution, not able to conduct electricity. Now, a weak electrolyte, like we talked about here, and we'll see in just a second, as I said, it mainly will stay together, but it will produce a few ions that are floating around in here. So there's a few ions that are actually floating around that solution. You can see the light bulb comes on, but kind of dim in terms of comparison to, say, non-electrolyte, where it doesn't come on. Here it did at least come on, but it isn't going to be very bright. But because it still has some ions that are floating around that solution, still able to conduct electricity a little bit. And a big difference, as you can see here, when we get to something that is a strong electrolyte. A strong electrolyte has a lot, pretty much all ions floating around, a lot of ions that are floating around that solution. And as you can see, the light bulb comes off very brightly here, conducts electricity really well because of that. And that's, you know, your main difference there in terms of conducting. And it, again, is those ions that are floating around that really allows it to conduct electricity. So, for example, if you took one of these sort of light bulbs with the electrodes and you stuck it into pure water, just pure water, H2O, nothing else in there, water itself is actually a pretty bad conductor of electricity because it really has no ions that are floating around in it. Let me be very clear again, the water coming out of your tap is not pure water, and you will electrocute yourself if you try to blow dry your hair in the shower or something like that. But they actually put ions into water to kind of clean it and stuff like that. So there's actually a lot of ions floating around in there, which is why kind of tap water, if you will, does conduct electricity. But technically, if you have just pure H2O, is not a very good conductor of electricity, again, because there's really no ions floating around to help sort of complete the circuit and stuff like that. Again, please do not blow dry your hair in the shower and electrocute yourself or anything like that. So let's talk about sort of how we could recognize these and really what each of these sort of things are. When we talk about a strong electrolyte, what we're talking about is something that pretty much once it goes for a swim in water will 100% break apart. So if you took some solid sodium chloride and you put it in water, what you would have in that water is 100% these ions. So 100% of what's floating around in that solution is the sodium ions and the chloride ions. You have absolutely none of these sodium chloride units still together in that solution. And that's why something like this is a very strong electrolyte, because you have generated a lot of ions in that solution very quickly. It definitely helps conduct electricity and everything, and we would expect, again, that light bulb to go off. Oddly though, right, if you took the light bulb and you stuck it into the sodium chloride before you actually put it in the water, it would not conduct electricity, because in the solid state, you have no ions floating around freely. So it's really that floating around freely in that solution that really does help conduct electricity. So again, if you kind of stuck it in there before the water, would not probably conduct. After the water and all those ions are free and liberated and kind of moving around, would conduct really well. So you can kind of think of a strong electrolyte, and you'll see it again in 200B as well when you talk about sort of strong acids and strong bases. It's kind of a one-way street. 100% everybody is heading to the product side, and on the product side are all of our ions there in the solution. And again, that's what's allowing it to conduct electricity really well. And that is, excuse me, that's different than a weak electrolyte. A weak electrolyte will actually mainly stay together. So unlike a strong electrolyte, when you put a weak electrolyte into solution, what's going to happen is the whole thing, for example, this is acetic acid. That's basically vinegar. It's a weak acid. And in solution, what you would mainly have is the actual acetic acid still together. So in solution, you would actually have that whole unit of acetic acid still together. But some of it will break apart. So it will produce a few of these ions that are floating around. And because it does produce a few of these ions, as we saw sort of in that light bulb example, it's able to turn on the light bulb, but it's a lot dimmer than, say, our strong electrolyte, which was very, very bright. And you have basically both of those things in solution. And one way that you could sort of recognize that is by the arrows. So you can see that we have different types of arrows happening here than we do up here. And these arrows mean that this reaction is basically a reversible reaction. And a reversible reaction, as we'll see on this page, is one really where there is basically two directions. There is a forward direction, which goes from reactants to products. And there's a reverse direction that goes from products back to reactants. And at some point, the rate of each of those things, the rate of the forward direction will equal the rate of the reverse direction, and you'll get what is known as chemical equilibrium, or pretty much everything you talk about in 200B is the entire semester of that. But it's basically these reversible reactions that will reach equilibrium, and you have kind of a two-way street. So like a strong electrolyte, it's a one-way street where we get all ions. Here is kind of a two-way street where we're mainly, kind of going this way and keeping everything together. So again, mainly that whole sort of molecule will stay together. But again, because it's still able to produce a few ions in that solution, it again allows it to conduct electricity. And that's really different than, again, at the last one that we sort of talked about there on the other page, which was that non-electrolyte. And again, that non-electrolyte, no ions, and thus no conducting of electricity. So again, like I said, something like sugar is a good example of that. You could definitely put sugar into water and it will dissolve. But because sugar is basically, again, made up of carbons, hydrogens, and oxygens, that is all covalent bonding. They're going to be sharing electrons. There's going to be no ions that are going to be produced in that case. And again, because of that lack of ions that are produced, we don't see the electrolyte conducting electricity. Any questions on that there?
Yeah, quick question. So like in sports drinks, what is the electrolyte? It's not, is it sugar?
Yeah, so electrolyte, it can be electrolytes can be, all kinds of things, like ions and stuff like that. Our electrolytes, they're basically like, ions that are floating around in there. So some of those have, different sort of like potassium, sodium, those type of things that are in there. And that's, basically what some of those electrolytes are. So they're really just anything that will basically sort of, in terms of our body, help kind of complete certain things that we need in terms of our body and our certain cells. We need certain sort of equivalents of ions floating around in our body to help keep sort of the osmotic pressure of cells and stuff sort of correct. And that's more what those guys have. They sort of replace some of those important ions and stuff that we need for that sort of process in our body. Not like you would conduct electricity yourself or anything like that. So that's more what those sort of electrolytes are for.
Thank you.
Yeah. So hydration is the process, you know, where we sort of use water, for example, to dissolve ions. So when we do put ions into solution, essentially what happens a lot of times when we dissolve something is this process of hydration. And basically because water is polar, there's a negative side and a positive side of water, positive side being the hydrogen, negative side being the oxygen. And again, the positive ions that go, say, into solution get surrounded by the negative side of oxygen, while the negative ions that go into solution get surrounded by the hydrogen side there, which is the positive side of water. That prevents two things from happening. It prevents them from sort of coming back together. So the water basically acts as almost like a buffer region where those two ions cannot get back to each other, because if they did get back to each other, they would want to make that solid. But it also allows something like an electrolyte, for example, to look like it has completely disappeared. And it doesn't really disappear, as you can see here in this picture. What essentially happens when we see something dissolve or disappear from our eyes, it's really just getting kind of worked into the water matrix, and we no longer can sort of visually see it because it's just surrounded by a lot of water molecules. And that's sort of the process of dissolving. We could only again see something if we took something like sodium chloride and put it in water. We would only be able to see it again if, you know, we evaporated off the water. And when we'd evaporate off the water, we essentially would be getting rid of all these water molecules. Right? And there would be nothing preventing those two ions from basically coming back together, and we would be able to see that solid again. So sometimes people think about when we dissolve something, it's like, oh, it disappeared. Again, really didn't disappear. It just sort of got worked into the water network. So non-electrolytes, as I talked about, and here's sort of an example of that, like sugar, again, will dissolve. You know, there's a lot of things that will dissolve in solution, but again, will not produce any ions, so will not conduct electricity. So here's some strong electrolytes over here. These are some strong acids. All these guys right here, that's hydrochloric acid, nitric acid, perchloric acid, sulfuric acid. Those are all strong acids. They 100% break apart in solution. Here's some strong bases, which also would 100% break apart. And pretty much any ionic compound is usually considered a strong electrolyte. These are some weak acids here. That's acetic acid, hydrofluoric acid, and nitrous acid. And again, in solution, these guys will mainly stay together, but will produce a little bit of ions. This guy right here, NH3, is a weak base, also will mainly stay together, but produce a little bit of ions. And these are some non-electrolytes, and you can see these non-electrolytes, for the most part, are a lot of these sort of non-metals together, right? So covalently bonding. So we have a lot of the sort of carbons, hydrogens, nitrogens, oxygens, and again, they will sort of dissolve in solution, but will not produce any ions and thus not conduct electricity. All right. So let's take a look at a certain type of reaction that, you know, a lot of times are important in terms of electrolytes, strong electrolytes, weak electrolytes, and sort of what we do with them. So the first type of reaction we're going to talk about is a precipitation reaction. And really a precipitation reaction falls under the big category of double displacement reactions. So double displacement reactions is really the sort of big category of type of reactions. And there's sort of different sort of subcategories, if you will, to those type of reactions. And the way that you can recognize a double displacement reaction is it has a general form of AB plus CD. And what each of these things are ionic compounds. So you basically have two ionic compounds on the reactant side. And what happens in a double displacement reaction is the two positive guys basically will switch partners. So the A will hook up with the D and make a new ionic compound, and the C will hook up with the B and make a second new ionic compound. And this is your classic double displacement reaction. And again, kind of the double displacement reaction, really the big sort of category. And what we're going to talk about now is a type of reaction which is known as a precipitation reaction. A precipitation reaction is really a double displacement reaction. The only difference is in a precipitation reaction, one of our products here will make a solid. So the big classification of this type of reaction is double displacement. A secondary classification of a reaction like this is what is known as a precipitation reaction. So this is an example of that. If we take some lead to nitrate and we react it with some sodium iodide, we will make lead 2 iodide and sodium nitrate. So you can see it. This is a positive negative guy. That's an ionic compound. This guy is a positive and negative guy. And ultimately what is happening here is our two positive guys are switching places. So the lead ends up with the iodide on the right-hand side, making a new positive negative guy. And the sodium ends up with the nitrate on the other side, making a second new positive guy. Now, the formation of that lead 2 iodide is a solid. It is this yellow solid that we see here in the test tube. And that is why it's also can be classified as a precipitation reaction, because essentially we have made a solid or a precipitate. And a precipitate, which is sometimes abbreviated PPT for precipitate, is some type of solid that's formed from the formation of our mixture of two solutions together. So basically when we mix two solutions together, we have a bunch of ions floating around, a bunch of positive and negative guys basically floating around. And in certain cases, some positive and negative guys will come together and basically come out of solution as this solid, which is again known as a precipitate. Now, what we see here is what is basically referred to as the molecular equation. So this is the balanced molecular equation. Now, we could also write another equation which really describes sort of what is happening in solution. So if we have sort of the test tube like we have over here, we could really describe sort of what is truly happening. And if we do that, because this guy is aqueous and this is an ionic compound, in solution, really that guy is not together. It's a strong electrolyte. So it would break apart into lead with a +2 charge, plus a couple of nitrates, each with a -1 charge. Again, that's breaking this guy up. Our sodium iodide, NaI, also an ionic compound, also a strong electrolyte, would break apart as well. And it would break apart in solution as 2 sodiums plus 2 iodides, distributing that 2 across there. Now, when we come to the other side and we make this solid is this yellow guy, which will basically come out as a solid. And what that basically means is it is not going to break apart. In order to make that solid, those 2 ions need to come together. And in that solution, it is staying together. So we would keep the solid together. And what that would leave us on the other side here is sodium nitrate, which is also a strong electrolyte, which will break apart as well. So I'm just going to write it underneath as I ran out a little bit of room there. Na plus and 2NO3 minus here. So this equation here, which let me just rewrite real quick, maybe a little bit better here. paste that there. And pop in my last guy there, 2NO3 minus, slightly better. All right, this equation here where we basically can break everybody apart into ions like it's happening basically in the beaker, the test tube, whatever it is another type of reaction. This is what is sometimes referred to as the total ionic equation or complete ionic equation. And in a total ionic equation, when we write it, what we want to write is everybody that is a strong electrolyte, you should break apart into ions. Things that are solid, liquid, or gas stay together. So you do not break apart anything that's a solid, liquid, or gas. You keep those guys together. Anything that's a strong electrolyte breaks apart into ions like we did. In addition, if you happen to come across a weak electrolyte, because a weak electrolyte mainly stays together in solution, you would not break that apart either. So that would stay together. So really, when you go to write the total ionic equation, you basically break apart everything that's a strong electrolyte that would be in solution, basically floating around as ions. Anything that is a weak electrolyte, a solid, liquid, or gas basically will stay together when you write this type of equation. And as you can see here, you do need to distribute. Oh, I see them. Coefficients as well across the ions when you do break them apart. Question on that equation right there. Okay. Now, when we get to sort of the total ionic equation, you should be able to look on both sides of the arrow, and you may be able to find some ions that look exactly the same. So if we happen to look here, if we look and we have two nitrates on the left-hand side, we have two nitrates on the right-hand side that look exactly the same. We also have two sodium ions on the left-hand side and two sodium ions on the right-hand side. When you find two ions or an ion that looks exactly the same on both sides, and by the way, if you do this correctly, you should end up with the same number of those ions on both sides. If you find yourself not the same number of ions on both sides, probably something's not so correct. These guys here are what are known as spectator ions. So if you are a spectator, like the name implies, you are pretty much just watching. You're not really participating. So what spectator ions are ions that they're there really just to balance out the charge. They're not really part of any sort of product that's being made, are really the main part of the reaction that's happening. So what we do with spectator ions is after we write our total ionic equation, we essentially cross out our spectator ions. And what that leaves you in terms of an equation is whatever is left over, which in this case would be lead with a +2 charge, plus 2 iodides, make PbI2. This equation here that we're left with after we get rid of the spectator ions is actually what's happening in this reaction. So when we actually mix the lead-2 nitrate with the sodium iodide, it is actually the lead-2 ion coming to find the iodide ion to form that yellow solid that we're making. And this equation here is what is sometimes referred to as the net ionic equation. And it really is the equation that pretty much cuts to the chase of what is really happening in this reaction. What is the sort of the main part of the reaction that is taking place? Question on any part of those equations there? Okay. So how do you know if you sort of put these two things together, if you put these two ions together, if you would expect to make a precipitate or not? And that's where we look at something that's known as solubility and solubility rules. So when we talk about solubility, solubility is the maximum amount of solute that will dissolve in a solvent at a given amount of temperature. And there are some solubility rules that we sort of follow to help us decide if we put a couple of ionic guys together, a positive and negative thing, would we expect that to make a solid? Would we expect it to make more of a solution? If we find something that is soluble, as we will see shortly here, based off of our solubility rules, what that essentially means is when we write the formula and we sort of go and put the symbol next to it, it will get the aqueous symbol. Aqueous, again, is basically a solution. It means that you would not expect any type of solid to form when that comes together. If we use the solubility rules and it tells us it's insoluble, what that typically would get is the solid symbol next to it, which obviously means we will make a solid or a precipitate would be expected to form. So as we'll see shortly here, when we look at something like lead 2 iodide, we would expect that solid to form based on the solubility rules. So let's take a look at some of these solubility rules and sort of talk about what they mean. So the first sort of table that we're looking at, and I might have moved some slides around, so this might be a little bit later on in your handout. I kind of moved them forward. So these are solubility rules that are things that are soluble in water. So what that means is, typically speaking, these are guys that should get the aqueous symbol next to it. It should not form a solid when they come together. So the first sort of one is pretty much anybody in group 1 of the periodic table. That's your lithium, your sodium, your potassium. So really group 1. And ammonium, which is NH4+. These guys are pretty much soluble in everything. And we know they're soluble in everything because there are certain exceptions that happen. And when we look at the exception category here, there are no exceptions. So what that means is, you know, as soon as you see something from group 1 on the periodic table or ammonium in it, you automatically know you could give that guy an aqueous symbol. It should not be a solid. There should be no solid that's formed. There's no exceptions. Same thing if you have something that has nitrate or acetate in it. If you see that in a formula, you 100% could probably be pretty safe to write aqueous next to that thing. It will not form any type of solid. It should always be a solution, and everything should sort of mix and be floating around. Now, if you have something that has chloride, bromide, or iodide in it, those things are always going to be aqueous. But different is there are some exceptions here. And the 3 exceptions are silver, that's mercury 1, and that's lead 2. So if you have something that is mercury 1, silver, or lead with chloride, bromide, and iodide, the opposite happens. So normally these things are aqueous, which means if you have one of these guys, it would become insoluble and expected to make a solid. So if you remember, what we just were looking at, we had PbI2. I, again, is normally soluble, but one of the exceptions is lead, which is the case here. So instead of it being soluble, like we saw there, it forms that yellow solid, and it's going to be insoluble. So if there is an exception, it basically does the opposite of what it normally does. So it normally is aqueous, opposite would be insoluble. If you have something that is sulfate, it typically is soluble, except for silver, lead, and some of our group 2 guys, calcium, strontium, and barium. Again, if you had any of these guys with sulfate, it would become a solid instead of aqueous. So these are some of the solubility rules for things that are soluble in water. Any questions on that so far? Now, there are some rules of things that are typically insoluble. So let's take a look at that guy. So this table here are things that are typically insoluble. So that means everybody here on the left typically is going to be insoluble and a solid should form. So hydroxide, if you see hydroxide in something, it should be insoluble, except for pretty much what we saw on the previous slide. Anybody in group 1 are ammonium. And if it is, it will then become soluble. So that's why when we take something like sodium hydroxide, which is a strong base, hydroxides are usually insoluble. Group 1 sodium there means that this guy would be aqueous in this case. Now, there are some that are slightly soluble, calcium hydroxide, strontium hydroxide, barium hydroxide. Most people consider slightly soluble as being more insoluble. So most people think of it as being more insoluble. So usually most of the time they'll consider it, leaning towards the solid side, but it can be aqueous. Things that have sulfide in it, S in it, is going to typically be solid. Again, our same sort of exceptions, group 1 and ammonium, and also kind of group 2 here, barium, strontium, and calcium. Again, these guys are going to be opposite on this side, which means they would become aqueous if you had any of those guys. So solid if you have hydroxide without anything on the right, solid if you have sulfide without anything on the right, and solid if you have carbonate or phosphate without anybody on the right, which again is group 1. So you can see that for the most part, the exceptions here in terms of solubility or things being insoluble is the same as our group 1 solubility here. So those are sort of the same sort of exceptions. Question on solubility rules there. All right, so why don't you try some here. So for each of these, take a minute or two, look at your solubility rules, decide whether or not each of these will be soluble or insoluble in water, and see what you come up with. Okay, so let's take a look here. So again, you may not be able to find perhaps both things listed in that table, but you can usually find at least one of those things to help you sort of make your decision. So let's take a look here at the first one. So the first one, we start with potassium hydroxide. And really the potassium is as far as you need to go. Potassium is group 1, which means it's pretty much soluble in everything. There's no exceptions, so we would expect this to be soluble because of the potassium. And we would expect this not to make a solid, and if you had a sort of give it a symbol, it should have the aqueous symbol kind of written next to it. You could also look at hydroxide, and if you look at your solubility rules, hydroxide is typically insoluble except when it's with somebody from group 1, which it is in this case. And again, that's why it would be soluble. Coming down here, we may not be able to find silver right off the bat, but we can find bromide or Br minus. And Br minus is typically soluble in everything except 3 exceptions, and one being silver, lead, and mercury here. And since it does have silver along with our bromide, it goes from being soluble to becoming insoluble, as it's the exception here. And we would expect it to form a solid here. So we would expect silver bromide to be a solid when it comes together. Question on those two so far. Taking a look here, again, may not be able to find calcium per se, but can find chloride. Chloride is right next to bromide, which means it's soluble in everybody except for the 3 that we listed above, which is silver, lead, and mercury 1. In this case, this is not an exception because it has calcium with it. So we would expect this to be soluble, and we would expect it to be aqueous in this case. At this point here, we could look at lead. Again, may not see lead, but definitely see nitrate in that first table that we looked at. Nitrate, which is NO3 minus, is pretty much soluble in everything, no exceptions. And because of that, that's pretty much as far as you have to go. As soon as you see that nitrate, you know you're going to get the aqueous symbol, and that thing is going to be soluble. Any question on those two there? Okay, so the last one, which is sulfate. Again, sulfate is typically soluble, but it does have some exceptions, and some of those exceptions are silver, calcium, strontium, barium, and our good friend lead there. So in this particular case, because the sulfate is attached to lead, which is one of the exceptions, it goes from being soluble normally to, in this case, being insoluble because of that connection, and we would expect a solid to be formed in that particular case. Question on how to use solubility rules and determining if something is going to be aqueous, solid, or any of those things. Okay. So let's try to put this together here with what we've been talking about, double displacement reactions. And so, for example, here, if we wanted to write some of these net ionic equations, we want to make sure that we write them correctly, and we want to make sure we balance them, and we want to make sure we get the right states, because that's going to be important in terms of getting to, say, a net ionic equation. So I'll let you try this one first here. Write the net ionic equation for silver nitrate and sodium chloride. Why don't we first just start with the molecular equation? So start with the molecular equation. So take a minute or two and write the molecular equation, not the net ionic equation. We'll get there together, but start with the molecular equation first. Also include the states using the solubility rules that we were talking about. And again, this slide might be a little bit off from your notes, somewhere a little bit later on, I think. Okay, so when you have this sort of situation, which happens a lot, you have really just the reactants. So silver nitrate plus sodium chloride. You want to make sure, as we talked about before, that you always start with the right formula. So hopefully at this point, you know what the formula for silver nitrate is. It is AgNO3, silver being +1, nitrate being -1. It's going to react with sodium chloride, which sodium is +1 and chloride is -1. So you just need one of each of those. Now, when we look at something like this, if you're not sure kind of what's going on, you want to sort of analyze with the two things that you got, and you hopefully should realize that this is a ionic compound, so a positive and negative. This guy is also an ionic compound, positive and negative. So that's going to help you predict what should go on the other side. Again, ultimately, this is a double displacement reaction, which means that our two positive guys are going to switch partners. Really important at this point is this is the part where people really screw up. Maybe not so much in this particular reaction, but it happens a lot. People try to balance the equation and write the formulas at the same time for the product side, and you don't want to do it in that order. The order you want to do it is correct formulas first and then balance. You'll be okay in this case probably, but there's a lot of times when people try to combine that. And what that means when you think about something like silver nitrate, it really is a silver ion that makes it up and a nitrate ion that makes it up. That has a +1 and -1. And when you think of sodium chloride, it really is a sodium ion that makes it up and a chloride ion. So what we're going to do is take the silver and the chloride and put it together properly. That is +1 and -1, which means we just need one of each of those guys. Plus the other two guys will come together, which is the sodium, which is +1, and the nitrate, which is -1, which should give us NaNO3. Any questions first off on how I got all of those guys there? Once you have all the correct formulas down, then you could balance it. And in this case, you'll be okay because I think it's all 1-to-1 here. So we have one silver on both sides, one chloride on both sides, one sodium on both sides, and one nitrate on both sides. So it actually is balanced here. Now we can use our solubility rules that we've been talking about to figure out, what is going on in terms of, are these things going to be aqueous? Are they going to be solid? So looking at silver nitrate, the nitrate part tells us it is always going to be soluble, so it should have the aqueous symbol next to it. Sodium chloride, the sodium is as far as we need to go. There's no exception, so that also should tell you it's going to be soluble. Silver chloride, chloride is soluble in everything like we saw, except for silver, lead, and mercury. And in this case, it is going to be opposite of that. And we are going to get a solid here on the silver chloride based on solubility rules. And lastly here, our sodium is really as far as we need to go, soluble in everything. Nitrate, also soluble in everything. So you could look at them both if you really wanted to. They both should be aqueous. Any questions on how I got the symbols soluble or insoluble? Now, this reaction is again under the big umbrella of double displacement reactions. It can also be classified as a precipitation reaction because it made a precipitate. They are both perfectly good classifications of this reaction. And as you can see, you can definitely have more than one classification for a reaction, depending on what you're looking at. So what we just wrote was the molecular equation. And if we wanted to get to the net ionic equation, we would break apart everybody here. So this would be silver that would break apart. We would get one nitrate. Our sodium chloride, which is a strong electrolyte, would break apart into ions. Our solid would stay together as silver chloride. Remember, solid, gas, liquid, weak electrolytes all stay together. And our sodium nitrate, which is a strong electrolyte, would also break apart here. And again, this equation that I just wrote would be known as the total ionic equation. So at this point, you can look on both sides like we talked about. You should be able to find some ions that look the same on both sides. So in the case here, again, it's going to be nitrate. Also going to be sodium. And these would be our spectator ions, which again, we would cancel out. And that's going to leave us the last equation, which is what we're looking for here. So this is our total ionic we just wrote. So our net ionic equation would be what's left over, and that is our silver ion, which is really coming together with our chloride ion here. And those two guys are going to combo to make this solid that forms, which is known as silver chloride. Question on any of those steps there? All right. So why don't you try another one here? Why don't you do this example, which should hopefully be next. So why don't you write all three equations with their states. So write the molecular equation, the total ionic, and the net ionic of this combination with their states. So take a couple of minutes here and see what you come up with. Three equations, identify the spectator ions and their states of everything, and see what you come up with. Okay, so let's take a look. So again, we want to make sure always you got things in words or something like that, or just half the reaction. Always important. First, the correct formulas, and then the balancing part. So we are taking a reaction of potassium carbonate. So potassium is +1, carbonate is -2, which means we should have K2CO3 when we put that together properly. Is reacting with nickel 2 chloride. So nickel with a Roman numeral 2 means the nickel has a +2 charge, and chloride is Cl minus. So in this case, we actually need 2 of the Cls. Yeah. Now, when we go to form what's on the other side, we want to figure out what type of reaction it is. And since we're only talking about double displacement so far, it is a double displacement reaction. But you could recognize it because, again, the potassium carbonate's a positive negative guy. The nickel 2 chloride also positive and negative. So what that means is our positive and negative guys, our two positive guys, are going to switch partners. So when we put together these things, you want to again make sure that you get the right formula. So although you may be tempted to use that 2 that's there, you shouldn't, because this is really K plus and carbonate, which is CO3 2 minus. This is really Ni2 plus and Cl minus, even though there's a 2 there. So it is these two guys that are going to come together, and these two guys are going to come together in the proper way, regardless of balancing. So this is very common where people screw up and put K2 Cl2 because they want to balance it as they're writing the formula. So the proper formula on this side should be KCl +1 and -1, and we should end up with 1 nickel and 1 carbonate will give us our proper ones. So this is the way that you want to make sure you do it. I can't tell you how many times people screw up by trying to balance it and write the formula at the same time. So formula first, and now that we have all the correct formulas, we could go and balance this thing. We have 1 carbonate on each side, 2 potassiums, good place to start. Put a 2 there. That gives me 2 potassiums, 2 chloride, which is what I need, and 1 nickel. And we are actually balanced at this point. Question on how I got to that formula. So again, I can't stress it enough that super common mistake people do is that I'm going to balance it while I'm doing it. I'm so concerned about all these extra 2s. We can now use our solubility rules to figure out if anything here is perhaps a solid. Potassium in our first guy is all we need to go. There's no exceptions, so that should be aqueous. Again, nickel we can't really find, but chloride we could find. Chloride is soluble in everything except for silver, lead, and mercury, which is not the case here. So this guy would be aqueous. Potassium chloride, again, potassium soluble in everything, really as far as you need to go. Nickel 2 carbonate. Now, carbonate is insoluble. There are some exceptions, but nickel is not one of the exceptions. So that means that we would expect this guy to be a solid. So this again is a double displacement reaction. It could also be classified as a precipitation reaction because we obviously made a solid or a precipitate here. This would represent the balanced molecular equation. Any questions on that part of it there? Now that you have the balanced molecular equation, you could write the total ionic equation by breaking it apart. So if we start here, we would bring the 2 to the front and have 2 potassiums plus a carbonate. The nickel 2 chloride would also break apart into nickel with a +2 charge. The 2 on the chloride comes to the front when you break it apart. And we get 2 chlorides. The 2 here for our potassium chloride on the other side gets distributed. So we have 2 potassiums and also 2 chlorides. And as we talked about before, our solid will stay together and we will be left with NiCO3. That's a solid. This is our total ionic equation here. Any questions on that one? We can now look for our spectator ions. Again, same ions, both sides. I see a couple of potassiums here. See a couple of potassiums over here. I also see a couple of chlorides on the left and a couple on the right. These again would be our spectator ions. So our spectator would be our potassium and our chloride ions. And when we cross those out, that's going to leave us our net ionic equation. What is really happening here is our nickel is going to react with our carbonate ion that's floating around. And those two guys are going to come together to make our nickel to carbonate solid that's going to form. And this would be our net ionic equation. Any questions on any of those steps there? Again, a double displacement reaction, sort of the big classification, more specifically a precipitation reaction that is happening. And again, really what's happening here is our nickel ion coming together with our carbonate ion. Any questions on that one there? Okay, so that's a lot of slides. So on these, why don't you just go with, let's just do the balanced equation here and see what you come up with. Again, do the states and see just the balanced molecular equation should be fine on these. Okay, so let's take a look here. Again, if you're not sure what type of reaction, you want to look at what you're starting with. So we got a positive, negative guy, positive, negative guy. That should scream to you double displacement sort of reaction. So again, what's going to happen is our two positive guys will switch partners. So when we look on this, we just want to think about the basic units that make that up. And that is basically K plus and Cl minus. Basic units that make this guy up is a silver ion with a +1 charge and a nitrate there with a -1 charge. So when we put these guys together, just like we did with nomenclature, we want to make sure we get the right formula that gets us to 0. So for the potassium and the nitrate, we just need one of each. And for our silver and chloride, we would also just need one of each. At this point, once we have all of the proper formulas, we could look for balancing. And in this particular case, I think we are balanced. We have one potassium on each side, one Cl on each side, one NO3 on each side, and one silver. So it is balanced. We want to look at solubility rules. We got aqueous already happening there. On the right-hand side, as soon as we see the potassium here, we know that it's going to be aqueous. And if that didn't convince you, the nitrate should convince you, based on solubility rules, that it will be aqueous. And then we have our silver and chloride. Looking at our chloride, it is soluble in everything except our good friend silver. So because silver is an exception, we would expect, again, the silver chloride here to be a solid. And again, this would be a double displacement reaction, also a precipitation reaction as well, because a precipitate was formed. So again, you could classify it really either way here. Just kind of depends on which one you're looking at. Any questions on that particular one? All right, so coming on our second one here, same deal. We got a positive, negative guy, positive, negative guy. So again, a double displacement reaction where both of these guys are going to separate and switch partners. Now, when we look at this, again, even though there's two sodiums there, the basic unit that makes it up is a sodium with a +1 charge, and the basic unit of S is a -2 charge on that sulfur. Basic units here of our calcium. Calcium has a +2 charge, and again, even though there's a 2 there, the basic unit is just a Cl minus. And again, that's important because when we do switch here, we want to make sure we start off with the correct formulas, which means when we put together the sodium and the chloride, it should be NaCl, not Na2Cl2. So it should be NaCl. And when we put together our calcium and our sulfur, +2 -2 means we should end up with one of each of those guys there. Any questions on how I got to those formulas there? Now that we have the right formulas down, this is the point where we want to balance it. And we can see we obviously have two sodiums on the left, only one on the right. So we do need to put a 2 in front of it. That 2 will also go for the chloride, which we also needed 2. And we have one calcium and one sulfur. So the 2 in front of the NaCl should balance it for us. And lastly here, we would look at some states. So sodium is soluble in everything. So that is going to be aqueous. And our calcium sulfide is also soluble in everything. Yes, it would be aqueous as well. Again, sulfur normally insoluble, but in the case of calcium, becomes soluble. So what does that mean? What is really happening here? What is really happening here is if we take it to our net ionic equation, which would be Na2Na plus our sulfide plus our calcium with all the proper states, Cl minus, we would also go to the other side and break apart. Everything here would break apart. Which means when we look to go for spectator ions, we have sodium on both sides. They cancel. We have sulfide on both sides, calcium on both sides, chloride on both sides. We have basically ions floating around. So technically speaking, this would actually be no reaction, right? We wouldn't see a precipitate form. It would look pretty much the same. You just have all the ions flying around in this particular case. So actually you would end up with no reaction in this case. Again, it would just look like a solution, basically. Just you wouldn't see anything obviously floating around. Question on that particular one there. Okay. And let's take a look here. One last one here. So why don't you write the equation on this one now that you are professionals? And again, here you could just write the molecular equation. Okay, so here we go. Same approach here. We're going to start with what they gave us, which is ammonium sulfate plus some lead 2 acetate. So there's a lot of letters on the board there, but if we look at it, it is a positive, negative, a positive and negative. So again, we have our basic double displacement reaction happening. Again, here we have a lot of extra 2s and stuff like that. So when you're trying to predict the other side, you want to think about just the basic units that make these things up. So the basic unit here would be NH4 plus, which is ammonium. And again, even though there's 2 of them, basic unit's just 1. Basic unit of sulfate is -2. The basic unit that makes up this guy here is going to be a lead with a +2 charge and a acetate with a -1 charge. Again, you can see I'm not concerned with all the extra 2s or anything like that. I want to make sure I first get the right formulas. So we're going to switch partners here. So these two guys are going to come together, followed by these two guys. So the important part here is because we took the basic units, we see it is +1 and -1 that's coming together, which means essentially we would have NH4, C2, H3O2, which is ammonium acetate. And when we put together our lead and our sulfate, +2 and -2 means we just need one of each of those guys as well. Any questions on how I got to those formulas? Again, do not try to balance and write the formulas. Otherwise, you will get the wrong formula. You'll be there all day trying to balance something that will never balance. So you want to make sure you don't do that. Now that we have the right formula, again here, this is the point where we balance it. And since we got some polyatomic ions happening here, we could start with those. We have 2 ammoniums on one side, so we'll put a 2 there. And that will also give us 2 acetates, which is what we need, and 1 of each of the other guys. So we're actually good at this point in terms of what we have balanced. So rewriting it so it's not super messy here. I can't guarantee that's going to turn out like that, but we'll see. Too many letters. All right, that's the whole alphabet. There we go. Just gonna go underneath. All right, so I don't squeeze it. All right, now that we have the equation balanced, we can look at our solubility rules. So starting with the first one here, that's ammonium, which there are no exceptions. So as soon as we see that, we are safe to write aqueous next to it. Looking at our lead, we might not be able to see it, but we will see acetate. Acetate is also soluble in everything, so that will give us an aqueous for that guy. Coming to our other side, we have the combination of both of those guys, which is going to give us aqueous for the ammonium acetate. And that leaves us sulfate. Sulfate is typically soluble, except for one of the exceptions would be our good friend lead here. And that will make a solid. And that would give us everybody here with their states and our properly balanced molecular equation. Any questions on that there? Okay, so we'll stop here for lecture. And a couple reminders, as was an earlier question, our exam is scheduled for 1 week from today. And it is going to be on, should be on all of that bonding stuff. So that should be chapter 3 and 4. It should also be on the nomenclature, which was the last part of chapter 3. And I believe it should be on part of chapter 5, which should be moles, Avogadro's number, empirical and molecular formulas. So that's what it should be on there. So like normal, like our first exam and everything else we've been doing, we'll take it. I think we'll probably take it during lab time like we did the last one. And again, you'll take it through proctoral. It'll be a combination like the first exam. There'll be some multiple choice questions, which you don't have to show work for. And then there'll be a sort of a written part where on some of those questions, you will obviously have to upload some work, kind of like the quiz where there were some Lewis structures, but I'm assuming it's going to be on there and that type of stuff. Again, you'll be given a periodic table, any type of conversions and stuff like that. But as we talked about, you need to know the geometry, obviously, and those polyatomic ions and stuff like that will not be provided for you. So you do need to know those guys. Any questions on any of that stuff there? Okay, so we'll take a little break. We'll go to lab at 7:15, and we'll talk about the lab. And we might just finish up a few more slides on this since it kind of relates to lab as well. So we'll probably lecture on a few more slides and talk about the lab, and then I think that will be it for the lab. All right, I'll see everybody about 7:15. Make sure you put here if you haven't done so, and get up and walk around maybe. Huh?
Thank you, Professor.
Thanks. I'll see you guys in a bit.